Okay, so this lesson in AP Calculus, AB is solving separable differential equations. And separable, I'm going to explain what separable means. And first order, okay? First order means we're talking about, initially we're talking about you're given a first derivative. Okay, so we'll talk about second order separable differential equations with initial conditions later. That'll be a second video. But the separable, okay, so before we've had equations where we've had dy dx equals 3x, right, just like that. So we can do that, right? You take the integral of both sides. If there's initial conditions, you put those values in, you solve for c, you're done. If there's x and y on this side, that makes it a bit trickier, right? You just had a question like that, and this is how you're going to do that question that you asked about. And so when we have x and y on the same side as part of the derivative, right? The slope fields are all wacky, right? They're a little bit strange. But this is what we're going to do. We're going to step one here. We're going to separate the differential with all of the x stuff on one side and all of the y stuff on the other side, okay? We're going to try and separate them. X and y, okay? Separate them. Now, we've talked a little bit about the Leibniz notation here and this differential. Now, this is not really a fraction, like a number divided by another number, but in some sense, we can view this as a ratio. And so we can actually manipulate this equation by separating the dy and the dx. So what we're going to do is we're going to multiply both sides by dx and multiply both sides by y. And we're going to get this. So the first step is to do this. Y dy equals x plus 1 dx. Okay, so we're just going to, it's like we're cross multiplying. We're going to get all the y stuff. So there's no x's on this side with the y's. And all the x stuff, there's no y's over here. We're going to separate them. Okay, that's step one. Everybody got that?
But what is
All right, so the question was, what is the dy dx again? And that is Leibniz notation for the derivative. So that means that the derivative of y with respect to x is actually defined as x plus 1 over y. So the derivative is explained in terms of x and y. Now, the other question was, don't we usually have an integral with the dy? And yes, not always. Like sometimes we have the summation, right, which kind of led us to the Riemann sums. But this is going to set up the fact that we are going to be able to integrate both sides. Okay? So once you separate this equation, then you're going to integrate. So that's where the elongated s, the integral sign, comes in. You're going to integrate both sides and get rid of this differential. So now this is a pair. The integral sign and the dy and the integral sign and the dx. So now we're going to be able to integrate to get rid of the dy and the dx in a sense. So step 2, integrate both sides. And I'm going to talk about the c as well, okay? So if we integrate both sides, we simply find the antiderivative of whatever this this function is. Find the antiderivative, right? So this is going to be what? This is y to the 1 right now. So what's it going to be? How do I find the antiderivative of that? Add 1 to the exponent and divide by the new exponent. So kind of 1/2. Does that make sense? So you take the derivative of that, then you end up with just y. Okay. All right, that's good. And now, if this is not a definite integral, so we do the plus c, right? I'm going to explain this c in a minute, what we do there. So derivative here too, this is 1/2 x squared plus what? Plus x, right? Because a 1 would the antiderivative would be x. And then plus c. Now, we're good there? Okay, that's just antiderivative. Okay, integrate. Now, the only one c I have noted here, and we're going to come back to these steps, but you might say, why is there only one c? Because I see 2 c's there. Now, the c's are not identical per se, but what we're going to do is we're going to roll these two constants together into one, and we're just going to show the constant as one constant. So think about it. If this was anything plus 2 and this was plus 7, right? We could take this 2 over here, and this constant would be plus 5. right? So we could write two constants, because they're like terms, as 1. And that's what we're going to do. And so some students are kind of freaked out when I do this, but basically, we're just going to drop that. Just a constant on one side. So this constant, which was part of the two constants, is now, they're all rolled into 1. And for our purposes, it doesn't matter if we separate that constant into two parts or just have it as 1. Okay? Okay? Yeah, you can pick either one, either side. You can put the C over here or the C over there. Okay? All right, so I'll let you just digest this, okay? Because some of you are still giving me a funny face. But we're going to roll the two constants into 1. So now we're going to do, because there are initial conditions in this question, see? The initial conditions is f of 0 equals negative 2, which means that x equals 0 and y equals negative 2, right? So immediately we're going to solve for c. And so that's what step 3 is. Okay? Solve for c using initial conditions. And we want to do that right away. And so what do we have? We have 1/2, and we said that that y value was negative 2. So we're going to put negative 2 there. 1/2, the x value we said was 0. So it's going to be 0 squared plus 0 plus c. All right. So this is 4. Half of 4 is 2. And that's 0 plus 0 equals c. So does that look right? C equals 2. All right. So if the constant is 2, now I can, and this is really important, now I can put the 2 in for the constant here, but I'm going to rewrite everything the same. So it's going to look like this. It's going to look like 1/2 y squared equals 1/2 x squared plus x plus 2. Now, that's step 3. I'm not quite done because the question says find the original function here that yields this derivative with this initial condition. That's what the question says. And so I need to actually isolate for y now. So it's important to solve for c before you isolate for y. And I'll explain that a bit further in another example that I'll do. But now we go ahead and we just solve for y. And so we can multiply everything by 2 here, both sides by 2. And we get this. Okay. And we're now going to take the square root of y. And when we take the square root, we would normally do a plus or minus, right? Now, is that the case? Do we do that? Well, this doesn't yield a function per se. This is two parts of a positive sort of radical looking graph, right? And then the negative part of it. So I think we did a question like this before. Maybe not. I know it's in another video. But how do I know which one to use? Because we have to use either the positive or the negative, just one. And so this is what you do. You look back to the original conditions, the initial conditions, and look at y. When x is 0, y has to be negative 2. Negative. So look at this. If I have 0 here, 0, 0, that's square root of 4 has to yield a negative 2. So the final answer is the negative version of this. Okay? And that is the solution to this question. Why negative? Okay, so one more time. If for this question we know, what do we know? What we know is that when x equals 0, y is negative 2 for this function. So this is representing the function right now. So if I put in 0, if I put 0 squared plus 2 times 0 plus 4, I get square root of 4, which is 2. Now, should it be positive or negative? The initial conditions say it has to be negative. Therefore, this description of the original function has to have this negative sign there. Yes?
What's the name of this chapter?
This section is called Solving Separable Differential Equations with Initial Conditions. And first order means that we are given the first derivative. I'm going to show you how to do this given the second derivative as well. Okay? How are we doing so far? Doing good?